Broadcom. So this will be presented by three people, Hemal, Karen Saram, and Moshe Bolusin. And the title is Thor, a 200 gig PCIe 4 Ethernet controller for mainstream HPC market. So let me briefly introduce all our three speakers. Hemal Shah is a distinguished engineer and system software standards architect in the Compute and Connectivity CCX division at Broadcom. He leads and manages a team of architects. Hemal is responsible for the definition of Ethernet NIC product architecture and software roadmap architecture of performance of NICs and smart NICs. And Karen Saram is VP of Architecture and ASICs for Broadcom CCX division. He leads a team of architects and silicon engineers in defining and designing industry-leading performance NICs, smart NICs, and compute offload engines. And Moshe Bolusin is system architect in the same CCX division at Broadcom. Moshe spearheaded the system architecture development of RoCE and congestion control in Broadcom NICs, involved in the definition of Ethernet NIC product architecture, performance NICs, and smart NICs, modeling and system simulations. So let's give a hearty welcome to all three of them. And Hemal and all, if you people can share your screen, I'll stop the screen sharing. Please share your screen and people can get started.
Sure. Can you hear me?
Yes. Yes.
Okay. So I'm going to share the screen and then we'll kick off with Karen, then Moshe will cover the middle portion and then I'll end.
Sure.
But I'll be sharing the slides.
Do you want to do the full presentation mode?
Yes. Do you see full presentation?
Yes. Yes.
Okay.
Yes. Looks good now.
All right.
Okay, so I'll
Karen.
kick us off. Okay, so this is Karen Schramm, VP of Engineering in the CCX division, and I'll be kicking off our discussion. So today we're going to be talking about, let's go to the next slide, Hemal. Today we're going to be talking about Thor, which is our 4th generation NIC based on the Nitro architecture. So Nitro in CCX refers to our high-speed data path. It's focused on low latency at high bandwidth. This is a new architecture. We restarted this architecture about 6 years ago and designed it specifically for large-scale data centers. Thor is the industry-leading production RNIC. It's got 200 gigabits of bandwidth and less than a microsecond of round-trip latency. Thor provides RDMA support in hardware and using open source software. And one of the core innovations in Thor is the congestion control algorithm that we use with RDMA. And you're going to hear a bit more about that from Moshe later in the talk. Next slide. So Ethernet. Ethernet is ubiquitous. It is everywhere. And this drives a lot of investment. Ethernet NIC and switch performance has been advancing at a really quick pace. It's faster than CPU performance, and it's faster than alternative transports like InfiniBand. Because of all the competition in Ethernet, it drives down the cost, and Ethernet tends to be much less expensive than other proprietary transports. Now, with the lower costs and the ease of deployment, and now comparable performance, which was not always true, Ethernet is being used in the majority of the largest 500 HPC clusters in the world. So we believe Ethernet is a great solution for HPC deployments. Let's take a look at the next slide. The core features that make us believe Ethernet is the right solution and Thor is a great fit is that we focused on performance, CPU efficiency, security, and application performance. So basic high performance is the 200 gig and 150 million packets per second. That's just the main core data path within the device. But as you look at the system solutions now, you'll see that CPUs are becoming a common bottleneck. We're running into caching issues and PCIe bandwidth. There's a number of areas. So high performance NICs now offer a large array of offloads, moving as much processing as possible off the software, out of the driver, and into the hardware on the NIC. And this includes offering kernel bypass. Security, that's obviously important across all aspects of technology today, and the NIC is no exception there. And one of the most important areas is that we focus on application performance, and that refers to the overall performance of the deployed application. And that's quite distinct from micro benchmarks, which are useful in some areas and for getting started, but can be confusing versus how the actual application is going to perform. So let's take a closer look at some of these features. Next slide. Regarding CPU efficiency, it's been discussed quite a bit recently that Moore's law is slowing down, and as we're trying to get more and more processing power out of the CPU, which is one of the most expensive parts of the server, often the most expensive part, it's important not to take too much of the CPU core processing power for the networking. So CPU efficiency is commonly measured in the NIC as the number of cores required to drive a particular bandwidth. And Thor, given all of the offloads that it provides, has led us to have a very efficient Linux driver, and we get significantly better performance. What that means is we're freeing up CPU cores that can be used for the main application, for the main workload. And that drives better overall utilization and better efficiency of the deployed server. Next slide. Regarding application performance, this is really the most important aspect of the NIC, and it doesn't always get the attention it might deserve. There are a number of recent papers on this topic of tail latency, and you'll see if you look around NIC technology, recent papers on congestion control, much more focus on the issue of tail latency. If you're running an application that does a round of distributed processing, like allreduce, what matters the most is the longest time. And being really fast at a few of them is not really going to improve the performance significantly. So we've just tried to distinguish between these micro benchmarks that may show really outstanding performance on a small atomic operation, but doesn't necessarily reflect that a distributed workload is going to perform well. We've built a cluster of about 64 nodes in our lab, and we're continuing to measure performance and look to improve what we can do in the NIC to get the best performance at the application level. Today, we're seeing quite good performance with Thor, and we plan to continue to invest in this area because it will have a, lower tail latency, less jitter. That's going to lead to better over performance of an application. Next slide. So we can't talk about technology without talking about security. We have a pretty strong solution in Thor. We have some of the industry leaders in security in our division. And while it's a hot topic across a broad range of technology, it's often a little bit harder to deploy good security than you might think. So in the NIC, we provide a range of services, which we tried to summarize on this slide. At the bottom, at the root of it all, is secure boot. So we can securely boot the firmware, authenticate the software, provide secure firmware updates. It's all built into the device, and there's quite a bit built into the hardware platform that provides those services. A couple members of our team are actually driving some of the security standards with our customers and across some organizations, including OCP and DMTF. Attestation is a newer feature, at least it's new to the broader market, but that feature allows an operator to verify that the hardware and the software that was deployed around the data center is exactly the hardware and software that they expected. And it's early days to have this broadly available, but we're at the forefront of defining how to do that. And also spend quite a bit of time just on lifecycle management, because as I said at the beginning, it's quite a bit easier to talk about security than it is to actually deploy it and manage it in the field. Next slide.
So I had a quick question before going forward. So in the previous slide, you had mentioned about cryptography. So are we able to do this at line rate, or is this only meant for like management traffic?
So in Thor, we have cryptographically protected firmware, authentication, attestation. Our next generation product called Stingray 2 has actually inline inline cryptography, like it can encrypt and decrypt packets at line rate as they go over the data path. So that's in our next product, but it's not yet in, it's not currently, inline encryption is not available in Thor.
Okay, no, thank you. That's very useful information.
Sure, glad to help. And then in addition to the core capabilities we just discussed, there's like a number of other capabilities. So Thor has some advanced features that include packet processing. The packet processing allows for flow identification, monitoring, sampling, editing, a wide range of capabilities that you can do on a per flow process, where you can identify a flow with any number of flexible fields pulled from a network header. We also have traffic management features that enables you to provide different levels of service and different rates by traffic type. There's a lot of flexibility in this, and it provides class of service scheduling across up to 8 classes at the network port, and then there's a number of per flow services and per VNIC services if you're using virtualization, such as SRIOV. We also support multi-host. Multi-host is relatively new. It's a feature that allows you to take a single NIC, split up the PCIe interface into 2 or 4 connections, and connect directly to the CPU. There's 2 ways that we've seen this used. The most common way is to build a server that's basically got 4 independent CPUs in it, or 2 independent CPUs in it, and connect directly to each of those. But we've also seen people looking at taking a dual socket server and directly connecting to each server, and this allows you to present the data directly to the cores to which it is destined. So both of those capabilities allow you to be more efficient, both with cost and then performance.
So a quick question on the multi-host support.
Sure.
From the application's perspective, will the application be able to tell that this is the same physical NIC, or will the application think that like I have 2 separate NICs to play with right now?
So if you connected both ports to the same, it would look like 2 separate NICs basically.
Okay.
For each interface, if you connected to 4 CPUs, they would each think they had their own NIC.
Okay, so like I'm coming at this from an HPC perspective. So what happens is that if the application thinks that I have 2 separate ports, this might lead to contention at the network level. So if there is some API which can be provided to for the application to figure out if I have two separate physical NICs or just one NIC in a multi-host fashion, we could do some interesting designs at the application level which can take advantage of it.
Sure, that's a good idea. Why don't you reach out to us after and we can talk about it?
Sure.
That'd be great. Okay, this is the last slide in my section. So if you're learning, would like to learn more about Thor, or you have any questions, please reach out. And at this point, I'm going to hand the talk over to Moshe.
Hi, everybody. So I will describe some of the RoCE features. We can move to the next slide. The RoCE, as you may know, is basically an InfiniBand transport that with the difference that it's running over a lower layer Ethernet rather than a lower layer InfiniBand. So it could work on the same network with other protocols such as TCP and so on over the commodity Ethernet switches. So Thor is supporting several features related to RoCE. I'll go over some of them and put some emphasis on one of the key network aspects, which is the congestion control and how the application will be impacted in terms of completion time and the performance due to possible congestion in the network. So the network performance for Thor is 200 gig. There are multiple options in terms of how many ports and what speed they can reach, going from 10 gigabit through 25, 40, 50, 100, and 200 gig. The total throughput is 200 gigabit per second bidirectional. We are supporting multiple physical function and virtual function on the PCI side, and also various features that Karen mentioned from the data center bridging standard, such as ETS, priority flow control, and so on. From the RoCE perspective for congestion control, we're using the RoCE v2 standard, the ECN marking, with CNPs, with congestion notification packets. We support the reliable connection and unreliable datagram services defined by the InfiniBand transport. And there is a wide range of page sizes for the system as well as for the PCI bar, and the very wide range of the possible size for the memory region and memory windows on the system. We also can go up to 1 million Q pairs in reliable connection, and 64K doorbell. This is the number of different applications that can access the NIC. We support shared receive queue to minimize the memory resources on the host, and 1 million completion queues on the NIC.
Moshe, I had a quick question, if you don't mind.
Sure.
So you mentioned that you have different doorbell page sizes, like from 4K to 4 kilobytes to 4 megabytes.
Yes.
What is the impact of these different page sizes on the application performance? So for instance, if I'm running a simple bandwidth benchmark with a doorbell page size of 4K versus 4 megabytes, what would the performance difference be?
That will not have a direct performance impact at all, the doorbell size itself. But because there is limitation on the overall doorbell size in the system, you may need to limit the total number of doorbell that you have if you're using larger doorbell page size, because each application will have to have, for security reason and isolation, will have to have its own pages. So that's the only impact. Yeah.
So how would one go about limiting this doorbell size? So like, how does that relate to the number of network resources I create or network resources I use?
the the amount of network resources you use, this part of it is really related to the total amount of bar size that you can allow on your system. So depending on the bar size you can allow on the system, you will be able to decide whether you want to use large pages because you don't need so many applications within this limit, or a smaller size if you need many more applications.
Okay. Okay.
Right.
Thank you.
Thank you. Sure. Let's go on to the next slide. Yeah, so some of the key features in RoCE that allow for good scale and good performance. From the network perspective, we support two different ways to handle congestion. One of them is well known, which is the second one on the list here, the probabilistic marking. The other one may be less known, and it is based on a similar protocol called DCTCP for deterministic marking, where above a certain threshold of Q level in the switch because of congestion, every packet is marked, which allow for a lower Q level overall, which I'll talk about later, and a good end-to-end latency through the network is experienced by other flows that do not contribute to the congestion. And I'll elaborate on that in the next few slides. The congestion control is scaling with the number of competing flows. It's all implemented in hardware. We also have Wookiee caching to optimize the access to the I/O bus on the system. So that because we do some interleaving between Q pairs, we don't want to serve one Q pair for a very long duration while others are still waiting. We do interleaving, but because we fetch Wookiees with unknown size of message delivery, we may only use the Wookiee, some of the Wookiees that we fetch over the PCI, and in order to optimize the I/O bus, we have caching for that, so that on the next iteration we could use the additional Wookiees, service them without having to waste another time the PCI bandwidth. We also support variable size Wookiee MTUs, sorry, because that's sometime coming to play when people want to use, for example, the full Ethernet packet size, like 1500 byte or possibly even higher. So this is completely flexible. What's the RoCE MTU size is, the number of DPIs that I mentioned already. We support asymmetric PFC for some applications, and of course implement the PFC watchdog that prevent possible very harming situation with PFC. In addition, we support shared protection domain and large shared memory region for application scaling. Next slide, please.
So, sorry, Moshe, just one further question. What are the benefits of a shared protection domain, and how can we use that, and similarly for shared memory regions?
Yeah, that's very specific to some application. If this is of interest to you, we should spend some time on that. You can reach us and we can talk about it. This is really have to do with some applications like database application, where multiple entities from the application side of things would want to use the same PD protection domain, and the application administrator or whoever run the overall system want to allow that.
Right.
Because in a normal situation, you don't want you want each application to have its own protection domain, and then all the resources like memory region QPs are isolated between the application. This is a way of allowing you to share the protection domain and have multiple application or multiple threads of the application manage these resources.
This would be of extreme interest to us, especially for dense communication patterns. So as I understand it, let's say if you have 8 processes on one given physical compute node, all the 8 processes can share a particular memory region / protection domain, and any process can act as a proxy and issue reads and writes for other processes. Is that correct?
That's pretty close to the way it works. Yes, Hemal, you wanna answer that?
Yeah, I think that's close to, and as Moshe was talking about, we can have more discussion on this. These are more like trusted cooperating processes, and by having single shared MR, it will be large contiguous, like terabytes of memory can be registered and shared by all of these processes, and then they can use single protection domain.
Sure. I think this would be of interest to us. I can follow up later. Thank you.
Thank you for the question. Very good question. Yeah, let's move on to the next slide. Hemal. So some of the things that are possible to do in terms of scale and deployment is the infrastructure scale, convergence of infrastructure, basically use of Ethernet and the IP protocol for multiple types of application in the network. Where you want to take advantage of, for some applications with the traditional protocols such as TCP, UDP, and so on. But at the same time, you want to allow some other application on the same network to use a more advanced or high performance protocols such as InfiniBand transport. And with this mechanism, this can be done on the same network. It avoids some of the complexity with an alternative solution such as iWarp, and it have a very large scale of SRIOV support for 1K virtual functions. In terms of software, at this point, we have a very simple driver model. We support the standard verbs, libverbs from OFED. And in terms of network management, we have what mentioned already, the ECN congestion control, which is part of the RoCE v2 standard. The implementation is focused on a very fast reaction and on flexibility or configurability of many of the parameters, as well as 2 different schemes or algorithms for congestion control, probabilistic and deterministic. And we also support telemetry, which is coming to play heavily in ability to manage the network and having a clearer view of what's actually going on in the network while it's operating. And the next subsection of my talk, Hemal, we can move to the next slide, is going to focus on the congestion control. So I'm going to describe here, a lot of people know about probabilistic congestion control. I'm going to provide the other mode that we support. And the main focus of this mode is to allow for a very low queue level build up in the switch. So whenever there is excess capacity coming into the switch that where the destination is the same destination, then of course, if we have, for example, multiple 100 gig coming into the switch and all the traffic is wanting to go to one single destination that is also 100 gig, then of course the excess capacity have to be stored, and it will be stored in the switch. However, when it is stored in the switch, there are side effects to that, and the side effects could be that just exhausting the switch buffer. And in that case, if PFC is enabled on the network, then PFC will be asserted by the switch and will be stopping the multiple machines. But PFC by itself, although it will prevent from the switch to continue build up or prevent packet drop and is reliable, is not granular in terms of the feedback it gives to the particular flows that create the congestion. It more coarse in the sense that it will just stop everything that is coming from a particular host on a certain class of service. It just stop everything, even if it's a priority flow control and not pause. Because there are only 8, the number of priorities that you can have is only 8. Congestion control, on the other side, will be able to give feedback to particular flows. So even if you have hundreds or thousands of flow coming on the same class of service from the same host, only those that are involved in the congestion on a certain egress port towards the destination, only those will be slowing down their transmission to prevent the buildup of the buffer of the queue in the switch. What you see in the diagram above is basically the way that the protocol work. In the purple part of it, you see the marking threshold, which is very low. When I'm talking about very low, I'm referring to tens of kilobyte of buildup in the switch egress queue. And from that point on, every packet is ECN marked, and every packet will result in the receiver sending a congestion notification packet, which you see on the left side, back to the sender, and the sender will then respond by slowing down its transmission, and that happen on a queue pair or flow granularity. So every individual queue pair maintain its own state. It's a per QP or per flow, if you wish, state for the congestion control, and it managed in hardware individually. So only those flow that cause the buildup in the egress queue will slow down. But with this kind of protocol, because of the way the algorithm is implemented, similar to DCTCP, then the buildup is very, very limited to usually tens of kilobyte, and even in heavy congestion, no more than few hundred kilobyte. What the effect of that is twofold. One is that we are staying far from the point that PFC will have to be utilized. And again, PFC, if PFC is utilized, then we lose the granularity of penalizing only the flows that contribute to congestion, and it's a more coarse reaction. But there are more severe issues for PFC, like PFC propagation, where it could result in blocking a large part of the network if it's sustained for a long enough time. So we avoid this situation of having to utilize PFC even when we have multiple point of congestion with multiple senders that contribute to the buildup. And we will see some results related to that. On the right side, you see some of the high-level description of the algorithm. I will not go into that. We could schedule sessions with individual sessions with those who are interested on how exactly it works, and we can move on to the next slide to describe some of the key benefits of this protocol. And of course, you could use the usual probabilistic based congestion control. But with this alternative method of congestion control, we can support very large number of competing flow and still maintain very high utilization of the network while keeping, and that's the key, the egress queue peak level very low. This reduced the likelihood of reaching the PFC, like I said. And the other benefit of that is that it gives latency latency through the network, end-to-end latency through the network, as experienced by other applications that do not contribute to the congestion. Is very limited. And we will see some example charts in the next slide. The low marking threshold, together with the implementation of the algorithm on the sender side, gives a very quick reaction by all the flows that contribute to congestion, and it converged to a stable point or very low Q level in the switch and high utilization very quickly thanks to that. We also support probabilistic marking. With probabilistic marking, you could achieve similar result, except for some of the short or small Q level, which sometimes is a compromise of probabilistic marking. And with that, the Q level could rise to a significant level, both risking either drops or PFC assertion, and enlarging significantly the round trip time as experienced by other applications through the network. On the next slide, we can see a small demonstration. There's of course plenty of them, of what happened on the network if PFC is enabled in blue on the left side, versus what happened on the network if ECN is enabled with the DCTCP-like congestion control mechanism in terms of the round trip latency. So on the top left, you see a 16 node all-reduce halving doubling, which is involve both all-reduce operation and all-gather phase. What happened when only PFC enabled, and this chart is produced with a simple IB write lat IB performance tool that try to send short packets that are not involved in the congestion through the network between two nodes, and we measure the latency. And you can see that sometimes the latency, of course, is very low. But when there is congestion, we see these spikes that could rise up to 800 or even 1000 microsecond in terms of latency. And that is because with PFC, the queue could build up to a very significant level during congestion. And on the top right, we see what happened exactly in the same kind of simulation, not simulation, sorry, this is a testing with all-reduce halving doubling on 16 node, where we have the peaks rising to maybe 100, 120 microsecond at most, and allow other application to deliver messages very quickly through the network. Similarly, on the bottom, we see the 64 node on the left side with PFC. And here, because it's more node, we can see that the peak level on the switch could rise even farther, and we can experience a latency through the network of well over 1 millisecond, even approaching 2 milliseconds at times. And with PFC, we stay very, very close to what was achieved with the 60 node in this case, up to 200 microsecond overall latency through the network. So this concludes my part of the discussions. If there are any questions, I can ask if there are short answers I can give right now before we move to the last part of the presentation.
No, I do not see any questions right now. I guess we can come back to it later on. Maybe we can move on.
All right, so Hemal, this is to you.
Hey, thanks, Moshe. So we covered the Thor architecture at large, and then Moshe went into the RoCE feature set, advanced features, especially the congestion control, where we had number of features and enhancements to address the large scale deployment. I'm going to spend in this last section primarily go over the software and firmware component for RoCE, and then we'll conclude the talk, and we can take additional questions at the end, as well as questions in between. So this is a view of Thor firmware architecture. what it is all the control plane, which is running inside Thor, is running on this embedded subsystem, which is consisting of multiple cores, which are ARM-based. These cores are designed for really small footprint environment, as not only it's a cost consciousness, but also you want to have more responsive kind of firmware. You don't need to have any OS environment. Primarily, it runs really thin RTOS type of runtime environment to facilitate control plane tasks, and all these firmware images that are running on these CPUs that are embedded are basically providing a set of services, and those services are through those firmware images, which are all securely booted and securely updated. And this services consist of, we abstract all the hardware resources are abstracted from the driver, which are the client. We call this abstraction layer as hardware resource manager. This provides isolation, protection, virtualization, as well as abstraction of hardware resources. So each function, PCIe function driver, basically is a client to that service. Additionally, there are embedded services for DCBX, LLDP, which is primarily for the network control aspect. There is also embedded agent to provide integration with network policy configuration. And then with any server, you have out-of-band management that is done through shared NIC model. So you need to support a number of sideband management protocol and interfaces. Those are also running as a management service on those embedded core. So in summary, that's the firmware architecture. It's a set of services securely running on embedded subsystem, and all images are securely booted and updated securely. And it provides a level of hardware abstraction to the host as well as the guest drivers. So with that firmware architecture, which supports the control plane, this is the Thor RoCE software for Linux. And basically, this is it builds on the standard open source stack. It supports a host OS environment, or it could be a VM or a container. The underlying stack stays the same, whether you're using this over a physical function or virtual function. And it's pretty much aligned with our philosophy has been to it provide the components which are aligned with the Linux kernel and open source community. All kernel modules are upstream and user libraries are submitted through OFED and Linux RDMA. So basically what you see in here, along with those RDMA core components which come from the Linux RDMA, which includes the IB verbs as well as the IB core components. We have for Thor the user mode library, which is libbnxdre, and then kernel mode driver, which is coupled with the NIC driver, which provides the standard L2 services for TCP/IP and other network traffic. And all the control plane services are provided by the control plane firmware running inside the device. So this shows the software components view of what Thor RoCE software provides for Linux. And before I go to the next slide, if there's any question here, let me ask.
No, I don't see any questions. I think we can move on.
Okay. So on top of those Linux software component we are talking about specifically here, this is a view of what gets upstream. So along with other core components, we upstream both the user space library as well as the kernel mode driver. And what from the OFED standpoint, it is also part of the package. So those who are using OFED package, it doesn't require the latest kernel. They also get benefit of having these components from Broadcom, Thor, device-related software support included in the OFED package. So this has been upstream and available both through the RDMA core as well as OFED. And basically MVAPISH2 builds on top of that. It leverages that standard VERP stack, and what we do is through the VERP provider, we are enabling MVAPISH2 today. Basically, MPI applications, they don't need any modification. They can run unmodified. No, there are no proprietary extensions here. So you can leverage pretty much all the components I mentioned for MVAPISH2 running an MPI application, leveraging all those. And tomorrow we have another 30-minute talk where we'll get into some of the preliminary results on what we have seen with MPI application. So we'll go over that tomorrow. Another thing I want to mention here, in addition to MVAPISH2 support, is the GPU direct support. So here also the idea is to keep it simple and support the open source model. So it's based on peer memory model. And what it is in this case, by having another module, which is registered with the IB core as a client driver, what you are doing is in that module basically exports function for the GPU peer memory. And then also it provides the user memory mapping for different GPU vendor drivers. So this enables GPU direct support. The IB peer memory module is basically sitting in between. It's providing also mapping between the IB user memory structures and the peer memory structure. So those are transparent to a user. And combining that with other components that come with the RDMA core, including user library and kernel mode driver, this enables GPU direct support using Thor. So this also with MPI application that are using underneath GPU direct can leverage all the features that Thor offers, as well as combine that with the GPU direct model. So just to summarize, from the standard VERPs support to MVAPISH2 to GPU direct, the software component what we have, they're all open source and upstream. And that has been the support for Thor and Broadcom philosophy. There is no proprietary extension needed. And it supports a variety of applications. Let me ask, are there any questions on the software and ecosystem we have enabled with Thor?
So just a quick question. So what sort of operations does Thor's GPU direct support? So does it support the full range of RDMA, read, write, atomic, and everything, or is there a subset of it which it supports?
It supports all your standard read, write, and atomics. If for more details, we can tell you exactly what operations are supported.
Okay.
And this is one of our goal is to integrate this with MVAPISH2 GDR, so that it enables somebody using that library to get the GPU direct support for MPI application.
Okay. So do you have some low-level benchmarks I mean, you mentioned that all of this has been pushed to the RDMA core Git, right? So did you guys also update any of the benchmarks like read lat or write lat or send lat to perform device-to-device transfers using the GPU drive support?
We didn't do any specific benchmark changes for that, and tomorrow in our session we can have some more discussion on this. We'll share some initial data that we have on benchmarks as well as some MPI applications. We don't have data for GPU direct yet because MVAP-2 GDR support is what we are working on, but once we have, we can talk about that also.
Sure. There is a follow-up question on Q&A. So the question is, any suggestions on switch compatibility?
So from, and Moshe did go into all the implementation of Thor RoCE feature set is, as you can see, is leveraging the standard switch infrastructure, whether it's ECN based, PFC, so all the switch-like communication that is needed. That being said, we test significantly for end-to-end with our own switch families, including Tomahawk. And one of the benefit of having tested with Broadcom switches, they have the same SerDes used on both NIC and switches. The settings, end-to-end kind of configuration, which just works out of the box. And there has been significant feedback from customer that they would like to see RoCE deployment more as from the network infrastructure standpoint than just the endpoint. So we have tested with multiple, we can provide a whole list of switches that's been tested, including our own ODM as well as switch vendors, variety of them. We have tested that with different, just the PFC only, PFC with congestion control combined, as well as congestion control only.
Okay, thank you. So there's another question from Talak Networks. How does the probabilistic ECN setting and CNP generation compare to DC QCN?
So I think, Moshe, this may be more detailed.
Yeah.
Why don't we follow up on that? But Moshe, you want to do something quickly?
Yeah, quickly. The main difference is in the queue level, build-up level, and the latency, the end-to-end latency through the switch. The probabilistic marking could, especially when there are many congesting flow, result in a pretty significant buildup of the queue level during congestion. And while with the DCTCP-like algorithm, the deterministic marking, the queue level will remain very, very low, and the latency through the switch will remain low. That's the main difference.
Thank you. There is one more question. Is there corresponding new generation merchant silicon for switches to match with Thor NICs?
Yeah, so we recommend, it's public Tomahawk 3, that's Broadcom. And that when we talk about end-to-end, that's what we do primarily a lot of our testing and results, performance result collection with Thor and Tomahawk 3. So that's the recommendation.
Thank you.
Okay, really good questions. Let me then go to this last one just to summarize. So in this talk initially, as you heard Karen mentioning about Thor's leadership in industry's first PCIe Gen 4 200 gig controller, and we went over a number of feature set, including our integrated flow processing, traffic management, QoS, security features. It's basically targeted towards market where the RoCE feature set that Moshe went over is for the mainstream market where HPC applications are also running, and it enables Ethernet for that low latency, high bandwidth app. And all the feature set we went over is extensive set of RDMA features. They are designed for enabling that mainstream HPC market. And then finally, I went over the software framework. Our philosophy has been to enable standard software framework without requiring any proprietary extension, and continue to work with the open source community to enhance those frameworks. Yeah, so with that, I'll conclude the talk here.
Thank you. Are there any follow-up questions? No, I think that's about all the questions that are there. So let's thank the speakers for the wonderful tutorial. And Hemal and Moshe, I can follow up with you offline about the other discussions that we had about shared memory windows and things like that. So I'd be very interested in trying out those features.
Sure. Yeah, and I want to thank everybody. Really good set of questions, and reach out to us if you have any follow-on questions.
Yes, thanks for your interest.
Thank you. Thank you.